In this video, we will be talking about quality and how we ensure our systems have it. Now, I'm sure you have a conception of what a quality product is and would know a quality product when you see one. So, here we have two cars, and instinctively one exudes quality and the other does not. Surely no one would have trouble identifying the quality product. But if pressed to identify what makes one a quality car and the other not, you may have more difficulty.
The problem in pinning down whether something is a quality product is you have to know what quality is in the first place. And in the context of engineering, quality is a very precise definition. Quality is the property of a system, or indeed any product possesses, when it complies with the requirements.
So, if the requirement is for a two-door road legal car that can carry 4 people and exceed the speed limit, then both these cars actually have equal quality.
The process of proving that a system has quality is called verification, and it is showing that the customers, showing to the customers that they're getting what they have asked for.
Yes, Bob, and we've already used that term before, but we've also used the term validation. And I think we need to make sure that both those concepts are firmly defined. So here's a little story that makes the point. So we have a young system engineering student who meets a handsome young man and they fall in love. Now, by happy circumstance, this young man happens to have quite a bit of money, so they not only can think about buying a house, they can actually think about building the house of their dreams. So, being a system engineering student, she knows what to do. She lays out what they need in their dream little love nest in a specification. This they give to a builder, and the builder builds the house. Are they happy? Well, of course not. The house doesn't have a door. But, says the builder, your specification didn't ask for a door. And this comparison between what has been built and the specification is what is known as verification. But of course, what ultimately matters is the comparison between what is built and the need. And that process of comparison is called validation.
So, verification is the process of ensuring that what is designed and built meets the requirements, as outlined in the requirement specification. But what if there is a fault in the requirement specification? That is, when a product meets its specification, but does not meet the purpose or objectives, and hence the need. Validation is a process of assessing whether something that has been made to a requirement specification will actually meet the purpose. In other words, to do the job the customer really wants. This relationship is shown by something called the V diagram, or V model. It's a simplified version shown here, V being for verification and validation. It's a simple way to visualize the quality processes in the system engineering environment. Although it's a general model for any development program, it's particularly used in software projects. On the downstroke on the left-hand side are the design phases of the life cycle. And the last things to be designed are the components, which are of course the first things to be built. So the flow is now on the upstroke of the V, and these components need to be tested against what they should be. And as we go further up the V, the other build and operation activities are listed. And at each stage on the upstroke, what has been produced has to be verified to make sure it matches what was intended in the design processes on the downstroke, ending with validation. One failing of this sort of V diagram is that these activities are not in the sequence of the waterfall cycle, and you will see many comparisons for V models versus waterfall models on the web. The point is that both attempt to model the development process. For developing a time flow of activities, for development program planning, the life cycle waterfall is the most commonly used, but the V diagram can be used as a tool to aid development of a verification plan. that defines the activities that can be placed in the overall development program defined by the classic lifecycle.
This video is primarily about verification, that is, the means of proving quality, that it meets the specification. But before we look at that, we should briefly consider validation. If you look at the V diagram, validation may seem to be an operational phase activity because traditionally it involves both the players and the stakeholders comparing the system as built and operated with its objectives. Obviously, it's too late to change the system itself. The idea being that this validation exercise would be a collection of lessons learnt for later projects, what's called retrospective validation. Well, this is all very well and useful, but of course it would be better to highlight discrepancies between the requirement specification and the need and purpose before we have built the system rather than afterwards. This is why we emphasise the importance of identifying need in the concept phase, as it is a separate thing from purpose and objectives, so that when we move on to the requirements, they will better reflect the need. But incorporating an effective validation process during the development phase of a life cycle has always been an elusive goal. At the lower levels, that is subsystem and unit, there is a different approach being introduced. Manufacturers of such units will be responding to requirement specifications from the overall system company, and they will be treating the unit or the subsystem as a system in its own right for their design purposes. The argument goes that in this case, the validation of the requirements can be undertaken during the design and build phases, and therefore corrections can be made to the requirement specification and the subsequent design before the unit is delivered. So, formal procedures, often involving system models, can be introduced to check possible solutions, not only against the specification, but also against the objectives. It was to improve the validation of the requirements in this context that Boeing introduced the Working Together initiative that we discussed in the requirements video. Using such innovations as the integral commentary in the requirement specification to enable validation processes to be undertaken. Another example of trying to get a validation process in before committing to the system design was a series of what were called validation studies on Skylon conducted around 2010. These were effectively mission models, but done after the requirement specification and the system design were effectively complete. The unique history of the Hotel Skylon concepts meant that the system design was in a very mature form, way past a simple feasibility design, although of course it was not yet in its final frozen form. That would be the outcome of the system design phase that's going to come later. It meant that we had time to explore using Skylon for the missions we intended to validate the requirements and the design against, for example, supporting space stations or returning to the Moon or going to Mars. Even the Scorpion project, which I'm currently involved in, is fundamentally a validation exercise on Skylon and the wider view of the future spaceflight that it represented. But while these attempts to what might be called pre-validation of the requirements or even the system design are worthy and valuable and remain one of the key concerns of current system engineering practice, in the end, true validation can only be done after the system is built and it is performing its real role in the real world.
So let's get back to verification. On this V diagram, you can see validation is explicitly mentioned, but not verification. And that is because there are two aspects of verification: qualification and acceptance, and you need both of these activities together for full verification. Qualification proves that if the system is built properly, the system will meet the requirement specification. In other words, qualification proves the design against the requirements. In the classical life cycle qualification acceptance. In the classical life cycle, qualification should be established at the critical design review prior to starting production. Verification of the system construction, that is, proving that each individual system produced meets the required specification, is called acceptance. Acceptance can be achieved by proving that the product is made to the qualified design, normally achieved by inspection. But alternatively, acceptance can be achieved by direct testing or proving the product achieves its required functions. Acceptance of the actual system by the customer is also sometimes called buy-off, and this is done at the delivery review board. It is clear that acceptance is an activity for every model or batch, every time that something is handed over to the customer. But acceptance testing has an additional legal implication, as the process is normally agreed with the customer at the contract start, and failure to meet these tests will normally lead to extra expense to correct the problem, and can also lead to the customer refusing to accept the product.
I think a story here about delivery review boards and acceptance testing may be in order. Back in the 80s, I was attending a critical design review for an antenna that was going to be used on later versions of a satellite on which I was one of the team. That review board had members from ESA, from British Aerospace and the contractor making the antenna, and there were maybe 15, 20 people at that meeting. Now, I was the only British Aerospace mechanical engineer, and I was called out of the meeting to attend another meeting that was going on at the same time, which was a delivery review board for an antenna that we were going to put on the first spacecraft. So this was a real antenna. This meeting was much smaller. It had a contracts officer and a quality engineer on both sides. So there were about 4 people in the meeting. And the quality engineer, the British Aerospace quality engineer, had found something he didn't like in the acceptance testing. And what he'd found was that during the vibration testing, which is testing we do because the satellite is going to get shaken up on the launch vehicle, and also vibration testing is a pretty good test of workmanship. Anyway, this antenna had been put on a shaker table and shaken as the acceptance testing asked for, and it had completely fallen apart. All the bolts had come undone and the antenna just disassembled on the vibration testing. This was because they had not solithaned, that is, locked the bolts in place, because later on in another test they wanted to adjust the antenna, and so they couldn't do that if they'd put the bolts in. So, of course, could we accept that? No, we can't accept a failed test like that. It turned out there was a whole rabbit hole about the acceptance testing they were doing and whether it was actually proving what they claimed it was proving. But the point here is that acceptance testing is important. Normally, as exemplified by the fact there were only 2 people, it's a somewhat sort of formal and rubber stamping occasion, but rarely it can be that acceptance testing can fail and the customer just says, no, I'm not accepting the system. Well, we're seeing that qualification and acceptance are both part of the overall verification programme, and that qualification proves the design and acceptance proves the product that we build each time we build it. But this doesn't need the same sort of testing for qualification and acceptance. We do different sorts of testing.
Yeah. The qualification proves that the product works, and you're allowed, for example, to destroy the test product in the process of doing that.
Yes, you make a special version of it and then you test it to destruction to know where your limits are and everything.
And you may do that for sub-assemblies and all the rest of it.
Mm.
You can't do that with acceptance.
I mean, a classic case here is crash testing cars,
yes,
to show that the design is crash worthy, but you can't crash test every car
that you're
going to sell to the customer.
The only time you're going to find out whether it really is crash worthy is when you run into a brick wall driving down the road and you can't afford to do that. And in fact, qualification, you may over-test certain items to demonstrate they've got adequate margin.
Yeah.
Again. But what acceptance is really doing is to say this is close enough to the qualification test model for us to be able to accept the data from the qualification test as valid for this.
Yes. And if you're a structural engineer, you will already have come across this concept, because you'll be stressing for both ultimate load and for proof loads.
Yes.
And the ultimate load is the load that you put on in the qualification testing to prove that it will meet the thing. The proof testing is exactly that. It proves the individual thing you've made in a way that you don't break it for subsequent use.
That's right. So it possibly in a proof test you will exceed the design stresses by a small fraction, like 10% or whatever. But you don't expect there to be permanent damage as a consequence of that.
Yeah.
And I think this business of permanent damage is one of the critical things in any acceptance test.
Yes.
You don't want to change the product in the process of accepting it.
Yes. To ensure quality, organisations have a separate department, which will be called something like product assurance or quality assurance or even quality control. This department covers verification, but also reliability and safety, which we will look at in later videos. It is normal for this department reporting structure to be independent of the main engineering departments, with a special reporting path to senior management, so they can act independently and more objectively in ensuring that product quality is maintained without the project management pressures of cost and schedule. Great play is often made by companies of the fact that their quality organisation reports directly to the managing director or the CEO and bypasses many levels of management. I'm a bit sceptical of this. In practice, this normally means that the quality guys get isolated, as the managing director or CEO never has time to deal with them at the detail required to make them effective, and they have no working middle management path like everybody else. Well, with that caveat, what does this department do? In the system design phase, the quality department take the requirements that hopefully have been written in testable ways, as we emphasised in the requirements video, and make a complete plan as to how they are going to prove every requirement, which in days gone by would have been in a document called a test plan. But the word test seems to be rather unfashionable now, partly because we don't always use traditional testing to prove we meet requirements, and partly because the word test has a connotation of uncertainty about the outcome. So nowadays the grander title verification plan is more often used, but they are essentially the same thing. The plan covers both qualification and acceptance, and the approach to each might be different. We've already seen a test of destruction is often used in qualification testing, but for obvious reasons is never done in acceptance testing. It's also quite common for acceptance to be based on simple inspection that the part is as designed, having proven that design in the qualification test process. This plan forms part of the system definition and is approved by the customer. This forms an agreement as to what constitutes adequate proof to avoid arguments at the end of the programme. But that doesn't mean that there won't be refinement of the plan, as the detailed design gives a clearer insight into what verification issues might arise. But this refinement rarely alters the underlying philosophy, such as what test models will be used in qualification. In outlining the verification plan, it is obvious the quality team will need to see and understand the system design as it evolves. After all, they need to know what they are testing. But they also create design requirements in their own right to enable the system to actually be tested. For example, to test the data system, they will need to connect to the data bus. To test voltages, they will need to have test points. For our structural testing, they will need a way to mount equipment and then apply loads. So, from the verification plan, the various tests and other verification processes can then be individually specified in test specifications outlining what the test needs to measure and with what accuracy, and finally what results would constitute a successful pass. The test specification is then turned into a test design, where how the test will be conducted and with what equipment is needed, and including any special test rigs, and these are all outlined in this document. Once this is defined, then finally test procedures can be written, which actually give instructions to the people who are conducting the test. Once the tests have been conducted, the results can be recorded in test reports. On the lower level items in particular, this can take the form of a predefined form, which is defined in the test procedure. This not only makes it cheaper to produce, but also makes it easier to digest in all the paperwork that is required at either the critical design review for qualification testing and the delivery review board for acceptance testing.
I think Mark may be getting a little ahead of things here. If you just design something complex and then build it and then test it, common sense will tell you that in the real world it will almost certainly fail. That's expensive, and it adds program delays, and it erodes customer confidence. All very bad things in the real world. What all this tells us is that while qualification is the end point of the development program for a new system, it is set, or should be set, by the functions defined as the system requirements at the very beginning, even before we've completed the initial design. Of course, in real life, there will be dialogue between the customer and contractor as the design evolves, establishing just what tests and demonstrations will constitute an effective demonstration. However, only the most confident or foolhardy system designer will assume that we can simply build the system and go straight into system qualification. This is why we have a development program. The purpose of a development program is to discover how parts of our system work in real life. In qualification, we expect the system to work perfectly, without any problems. Even when we over-test things like structures to find out when they break, we expect there to be a defined margin between the expected service maximum loads and the measured breaking point. And if that margin is there, then it's not a failure. So the point of the development program is to maximise the chances that there will be no issues revealed during the qualification process. It's the program of tests that are undertaken before formal qualification to reduce the risks of it failing, and therefore arises out of an analysis of risk. So, unlike qualification, in development we can expect failures, and we can learn from these failures the ways in which the real world does not behave in the same way as our models predict. We therefore need to look at what we mean by risk and how we manage the risk in a program. Development means admitting the risks in the design and establishing what those risks are and eliminating or at least minimising those risks. We therefore need to look at what we mean by risk and how we manage risk in a program. I measure risk in the way that the insurance people manage it. If we think of any undesirable events like rain on our garden party or an accident in your car, then insurers want to know two things. What is the probability of that event happening? And what are the cost consequences if it does happen? If you insure it, then the insurers will multiply those two numbers together and then add about 20% on top as their margin. We'll forget about that last bit here and just define this as risk equals the probability of an undesirable event multiplied by the cost consequences if it does happen. Clearly this is fine if we can produce good numbers for each of these factors. And in looking at a development program, we obviously start by looking for the nasty things that might give us trouble. After all, we have a product assurance people who are supposed to be doing just that. And if you're any good as a designer, you'll already be trying to second guess what they will come up with. But we are unlikely to have precise numbers for any of them that we can fit into this formula. So instead we categorise events in terms of their criticality and their probability in more general terms. Criticality is here defined as the extent to which a failure damages the system or leads to a loss of the objectives, in this case to achieve the qualification goals. We can now construct a chart looking like this. Here, both the probability and the criticality of the consequences have been defined in quite general, broad brush fashion. And the resulting risk, represented by the different coloured areas on the chart, is similarly identified by the general categories of high, medium or low. A low risk could be because it's very unlikely, like finding a sore-scaled viper in your washing machine, or because it may be quite common, like a red sock in the whitewash, but its consequences are trivial. A high risk is something that is both reasonably likely and has serious consequences, like faulty wiring in a washing machine shorting and causing a fire. And now we can begin to construct what is called a risk register. We think of every way in which the system can fail. This can be quite a fun part. And then you do this systematically, looking at it subsystem by subsystem or part by part. And for each item on your list, you give it a value according to the categories in the chart, for probability and for criticality. And the chart then tells you whether the risk is high, medium or low. Having done this, you can order the risks in order of importance. But rather than simply identifying what they are, you now need to identify what you should do about each risk. We're starting to build up a register of the risks now, and once development is underway, we will add another two columns. One column will be to keep a log of whether action has been taken on each item, and the final column will show how we verify not only that the action has been taken, but whether it's been effective in reducing or possibly eliminating the risk, a process we call risk retirement. This is the process by which we deal with risk in our design. It's a four-step process which involves risk identification, risk evaluation, risk mitigation, and risk retirement. The first two of these steps, identifying the risks in our proposed development and what we're going to do about it, form the basis of our development program. And the last two are the development program itself. We set out where the uncertainties are in our design, what we're going to do about it and when, and how we're going to verify that we've reduced the consequent risks to as low a value as we're able. This diagram summarises the process. The requirements represent the starting point for a new design. The design follows from the requirements, but the qualification plan also follows directly as a part of the requirements, either being set by the customer or the contractor or as an agreement between the two. And the qualification plan part of the overall verification plan may itself influence the design. After all, we need to design that we can demonstrate that the product meets the required qualification tests. But then, from the design solution, we create an integration plan, how we're going to build it, and a risk assessment, and the two together create a development plan, which we hope leads to the qualification and a qualified system. Just like the design activity, the development program starts with the system requirements. The qualification plan, which is part of the overall verification plan that proves that the design works, should match every requirement with a plan to show and prove the design meets it. While the risk register looks at the design as it evolves and assesses the risk that the design will not pass the test. It's important to realise that both the qualification plan and the risk assessment affect the design. The qualification plan and also the acceptance plan often require the design to incorporate features that enable the qualification test to be conducted, like electrical test ports, structural hardpoints for the test rigs, or access panels for test equipment. And as we've seen, the risk register requires the design to identify how the risk is to be assessed in the design through redesign or redundancy or material choice.
we've rather made it sound like the players only agree the qualification testing with the customer, and that the development testing and the development program is something that they keep to themselves. It's to get them before the customer arrives on the scene. But particularly in places where the customer is paying for the development program, they do normally take a close interest in both the risk register and the development program.
Yes. Well, the two are intimately linked. What the risk register tells you, among other things, is how you're doing on the development program.
Yeah.
It tells you what to develop, but it also tells you whether you've done the things and whether there are problems that you've not met.
Yeah.
And so, from the customer point of view, one of the things that it does is to assure you that he's going to get his product on time. But the other thing that it does is it warns you of things that you've discovered that you've not met yet, that you may have to include in the qualification program. If there's some phenomenon or a particular problem that come out of that, then then it will arise out of the risk register and the associated work that's done. And you probably need early warning so you can negotiate whatever the changes are needed to the qualification program.
Yeah.
It's not to some extent we say that the qualification program is set at the point where you write the requirements, but that's not entirely true because you don't know everything. So it's discoveries later on that can have an effect on that.
Yeah. That some particular aspects of the technology that's new or the design that means there's a special problem that you discover in the development testing, and the customer says, well, hang on a second, I want to make sure everything you sell me doesn't have that problem enshrined in it, so add this test in.
Yes.
Yeah. Normally at your cost.
It's always negotiable, this one. And there's always a little bit of poker takes place as to whose responsibility is, because change notes to the program are where the contractor makes his profit.
The development, qualification and then the acceptance activities lead to a wide variety of tests and models that we conduct those tests on. We saw the use of system demonstrators to test key elements of a system design and the use of prototypes of qualification in the requirements video. And of course, in acceptance testing, by definition, that has to be conducted on the actual system being delivered. There are a few special points that can be made about acceptance testing. It should be a comprehensive set of tests showing that the complete system meets the specification on delivery. An example would be pre-delivery test flights on an aircraft. But sometimes the acceptance testing duration is prolonged in order to burn in a component to cover any infant mortality issues, and we'll be considering the reason for that in the next video. So far in these lectures, we have laid emphasis on designing a product to meet the requirements defined in the requirement specification, a key principle of top-down system design. However, acceptance testing can introduce a complication. Many acceptance tests push the system a little beyond the system requirement to ensure that there can be no question about whether that requirement has been met. It's the same philosophy as the baker's dozen, where you supply 13 when only 12 are asked for. And of course, we must also ensure that any testing covers statistical variations in the build. So the logic of acceptance testing leads to the fact that in most cases the design case that is actually used when defining the system is the one that ensures the system passes these tests, and not the real-world environment that is defined in the requirement specification. Now, this constraint does not in theory apply to qualification testing, because damaging a qualification model can be acceptable. In practice, the need to do further testing on an expensive test model means that qualification loads can also end up being the design driver that is used when creating the system. So we have seen these three models before, but in reality the verification program can have many more models than this. For example, we could have what is called a structure model. Now, to qualify a structure which has been designed to be only just strong enough, and so therefore as light as possible, will mean that when we apply ultimate loads, that will almost certainly leave the structure unfit for any further use. So to qualify the structure, often a separate structure model is built. That is a structure built to the final drawings, but with mass dummies fitted as opposed to real other systems. This structure model then proves the design by undergoing ultimate load testing. Now, that means that the prototype model has a structure which is normally required to be functioning throughout a complete qualification program. The structure model is an example of the many different sorts of model that can be used during a qualification program. Other physical test models that can be used include breadboards, iron birds, thermal models, and the catch-all term engineering model. The verification plan will contain a model philosophy outlining which of these models will be built and whether they are part of the qualification process or part of the development program. Typically, structure and thermal models will be considered qualification exercise, and the other breadboards and engineering models will be considered part of design development, but this is not a fixed rule.
As we keep repeating, for every requirement we have to have defined a means to prove that it is met. We've been using the term testing in this context, and testing is undoubtedly the gold standard of verification methodologies. But the problem with testing is the cost of building the test article and then conducting the test themselves may be large. So in reality, there are many cases where we can verify a requirement without turning to a physical test procedure, and often means of cost and practicality, this is what we do. Aside from testing, there are three other classes of approaches to verification. You can have analysis based on mathematical model of one sort or another. We can have direct use of or similarity to parts that are already in use, called heritage. And we can have inspection, which means either direct measurement on the finished item or maintaining a detailed log of the materials and manufacture of the components in building up the system. These approaches are used for both aspects of verification, although of course some of these methods were better for qualification and others better for acceptance. Inspection, for example, is used to establish that the same quality of parts assembled in the same way as the qualification model have been used in the unit product offered for acceptance. Qualification can be argued on the basis of analysis and mathematical models, but this implies that you have a great deal of confidence in your understanding of the system, and it may need to be backed up by testing critical cases on real hardware to confirm, verify the modelling used. We will explore various aspects of modelling later in the course. The verified model may then be used to qualify variations from the basic design, such as upgrades or special additions. This sort of approach can lead to attempts to qualify designs by reference to previous designs and modelling. This approach is okay if everybody keeps a cool head. However, the excitement of potential massive cost savings with this approach, there is a danger of taking it too far, and caution is advised. Examples of mathematical modelling used for verification include mass properties qualified by a mass budget based on mass estimates based on drawings, propellant budgets based on qualified engine performance data and mission performance modelling, structure modifications based on a finite element model already checked against testing key stressing cases, and control system response based on dynamic modelling.
The next methodology is to use the design that has been used before and therefore claim qualification based on the successful history of past uses. The first constraint is that this can only clearly be used for qualification, that is to prove a design, and not an acceptance of each build of that design. Arguing qualification by heritage has clear attractions in terms of cost. A bit of paperwork and the job's done. It also has the allure that a long history of successful operations is clearly a better proof that it will work than any realistic test program. However, there is an enormous potential trap hidden in the concept of heritage qualification. A famous, very high-profile case of this going wrong is the first Ariane 5 launch in June 1996. The flight control unit had been taken from Ariane 4, a sensible thing to do as it had worked well in that role for over a decade. Of course, it would need new software, but they kept the changes to a minimum as they were arguing qualification by heritage and wanted to keep as close as possible to the flight-proven unit. And this is what happened when it first flew. A data conversion anomaly switched in a piece of old Ariane 4 code that was still in the system, and the flight controller now thought it was flying an Ariane 4, not an Ariane 5, and this was the result. What must be remembered is that qualification is a match between a design and a set of requirements. If the design is changed, then the qualification status is lost. That's clear and obvious. But what is often forgotten is that when the requirements change, the qualification status is just as lost as when the design changes. This brings us to the last verification approach, inspection. This is a classic quality technique. It's relatively cheap, it's non-destructive and reasonably effective. A part, once made, is compared to the manufacturing drawing and every measurement checked. The same process is used after any assembly operation and again checked against the assembly drawings. These inspections are conducted by inspectors who are never the person who does the work, and then the results are recorded in a build log. The main constraint of this method is that it only proves the thing being inspected meets the design. It does not directly prove that the design meets the requirement. So you can only use inspection for acceptance and never for qualification.
Right, thus far we've covered the basic elements of what quality is.
Yeah, but in the next few videos we're going to look at how you can implement quality into a system in a real program.